All right, we're going to get started on what I call the special topics. In the last lecture, I said I'm going to be covering some sections from chapters 11, 12, and 13. So today we're going to start with section 11.2 on perfect numbers. These are special types or special forms of numbers. So the objectives of this section, we're going to start with defining what a perfect number is and present some examples. Then we're going to give a necessary and sufficient conditions for a number to be an even perfect numbers. It turns out that the only known actually perfect numbers are even. There is no known odd perfect numbers. Then we're going to look at how we can generate actually even perfect numbers. Then we're going to look at a few properties of even perfect numbers. So let's get started. Because of some mystical beliefs, the Greeks called a number to be perfect if the number is the sum of its proper divisors. The positive proper divisors of a number means except the number itself. If the sum of these divisors is equal to n, such number they call them perfect numbers. So here is the formal definition. A positive number n is called a perfect number if n is equal to the sum of all positive divisors of n except n itself. Such positive divisors, we call them proper, okay, positive divisors. Actually, we can state this, and for convenience, this is equivalently n is a perfect number if and only if sigma of n, remember sigma of n is the sum of all positive divisors of n, is twice n, because we are counting n in this case. All right, so as I mentioned, these are known to the ancient Greeks, and let me sort of give some examples. The smallest actually perfect number is 6, is a perfect number. Because the divisors, positive divisors of 6 are 1 plus 2 plus 3, and this is equal to 6. Or equivalently, if we take sigma of 6, which is going to be 12, and this is twice times 6. The next perfect number is actually 28. All right, this one is perfect. And the divisors of 28, the positive divisors, 1, 2, 4, 7, and 14, and then 28. So the sum of these is equal 28. the Greeks knew of only actually 4 perfect numbers. That's the only numbers they were able to discover. And this is one of the reasons we call them probably perfect, because they are very scarce. It's unlike other types of numbers like prime or even and so on. These are much scarce than actually the other types of numbers. All right? So the ancients agree only know of 4 perfect numbers. And these are 6, 28, and the next number is 496, and the 4th number is 8,128. All right? Now, if I denote these by the P1 means the first perfect number, and call 28 the second perfect number, and 496 is the third, and the 4th, then the ancient Greeks actually made some conjectures by only considering these. All right? So they made conjectures. The first one is they said that if P sub n is the nth perfect number, n equal 1, 2, 3, and so on, then they conjecture then, so they said that P sub n has exactly n digits. For the number than u, this is correct. P1, it has 1 digit, 6. P2 has 2 digits, 2, 8. P3, 3 digits. P4, 4 digits. All right? We're going to examine data and find out that this conjecture was incorrect, in fact. The second conjecture they made, they say that those numbers, those perfect numbers, the way they end is their units. Here is 6, then we have 8, then we have 6, then we have 8. All right? So they conjecture that the perfect numbers ends alternately with 6 and 8 in this order. All right? And again, this is true for the 4 numbers in here. This is a very small sample, of course. It would be very hard to imagine that these conjectures were to be true. And in fact, they are not. All right? So for the first one, turns out that if you look at the P5, which is the 5th perfect number to be discovered, is, and this happens actually many, many years later, 5, 5, 0, 3, 3, 6. So this is the, this has, of course, has 8 digits. Not supposed to be 5. So this conjecture means this one is not correct. However, the number ends in 6, which is after the 8 in here. So B4 ends in 8, then the next number is supposed to be ending in 6, and this is true. However, this one is again found to be incorrect because B6, all right, it's supposed to be 8, because this one is 6 now, that alternately we should get 8, and this one, no, it does not end in 8. And this number is 8, 5, 8, 9, 8, 6, 9, 0, 5, 6. So it ends in 6, not 8. So this conjecture is also not correct. All right. However, the Greeks actually were, and this appears in Euclid's Elements, in the 9th book of Euclid, determine, if the number is a certain form, then it is perfect. All right? And then later on, Euler actually gave a completed sort of this theorem, which we're going to state next, which gives a necessary and sufficient condition for an even number to be perfect. All right? So this is our first theorem. (11.1), and this theorem is due to Euclid, actually, and Euler. We're going to indicate which direction, actually Euclid proved and which one is Euler proved. And it says that the positive number n is an even perfect number if and only if n has this form: 2 to the power k minus 1 multiplied by 2 to the k minus 1, where k is an integer bigger than or equal to 2, and 2 to the k minus 1 is a prime number. Alright, so there are two things in here. If I want to spell this one out, it means that we have first if this number 2 to the k minus 1 is prime, then n, which is equal to 2 to the k minus 1 times 2 to the k minus 1 in here is an even perfect number. Of course, it's even because it's a multiple of 2 here, and because of the k bigger than or equal to 1, so the exponent for the 2 here is going to be bigger than or equal to 1. So it's an even perfect number. And this is actually what Euclid proved. Okay, so this part of the proof is due to Euclid. The second part, it says that if n is an even perfect number, then n has this form, equal to 2 to the power k minus 1, 2 to the k minus 1, where k bigger than or equal to 2 and 2 to the p, 2 to the n, or to the k, sorry, minus 1 is a prime. Okay, so this is what this actually theorem, if you want to split it out like this. And this one, this proof is done by Burton. Stated n actually proved by Burton. All right, let's go ahead and do the proof. The proof is pretty straightforward. It's just apply very basic properties of sigma, the divisor function, sum of divisors function, and just a little bit of argument. So let's go with the first one. And this one is u. So we can assume that 2 to the k minus 1 is a prime. Again, where k bigger than or equal. Now, let n equal to this. And we're going to take sigma of this. All right. First of all, since the greatest common divisor of 2 to the k minus 1, which is definitely it's an even integer, and 2 to the k minus 1 it is odd. These are relatively prime, so this is equal to 4. So we're going to apply sigma, the sum of divisors. And because this is multiplicative, and these are relatively prime, then we can take sigma of the first factor times sigma of the second. Now, the first factor, because it's a power of 2, the divisor is going to be 1, 2, 2 squared up to 2 to the power k minus 1. So this one is going to be 1 plus 2. 2 squared, and so on. Now, the sigma of the other number, this one, under our assumption, this is a prime. So it has only 2 divisors, which is 1 and the number itself. So this means that this one is going to be 1 plus the number itself. All right? Now, the first sum, this one is a geometric progression, and we can simplify it to simple form rather than this finite sum. From here, so this is equal 2 to the k minus 1 over 2 minus 1 multiplied by 1 plus 2 to the k minus 1, that's just 2 to the k. And first part becomes 2 to the k minus 1 times 2 to the k, which I can write as 2 to the k minus 1, together give me 2 to the k, and then 2 to the k minus 1 like this. However, this one is n, and so we end up with 2n, and this is exactly what it means for n to be perfect. So this implies n is a perfect number. All right. The second direction, opposite direction, is as easy as this, about. Probably a little trickier, but it's not any much harder. And now let's assume we're going this way, and this is Euler's argument or. So this time we're going to assume that n be an even perfect number. And we're going to represent n, since it is even, it must have the prime 2 to the k minus 1. I'm going to write it this way, multiplied by m. All right? Now, I know that the form of m, we can, of course, find out it must be 2 to the k minus 1. All right? So we're going to do this where k, again, it needs to be bigger than or equal to 2 in order to have a 2 here to make it even. And m bigger than or equal to 1 is odd. In fact, it could be 1, okay? Still make this is an even number. Now, perfect, of course, that's another thing. It's not going to be. All right, now let's look at sigma of n, since we start with since n is a perfect number, this implies that sigma of n is equal to. All right, well, let's take sigma of n as sigma of 2 to the k minus 1 multiplied by n. Similarly, the 2 to the k minus 1 and m are relatively prime, so this is also multiplicative. So we get sigma 2 k minus 1 multiplied by sigma of n. And similarly, we simplify this to becomes 2 to the k. Right, like we did before, minus 1. Or times sigma of n. But we say that also this is equal to n, which is 2 times 2 to the k minus 1 times n. Oh, let's write this down in here. So we have that this equation, 2 to the k minus 1 sigma of m is equal to the k times n. From here, we can say that sigma of m is equal to 2 to the k m divided by 2 to the k minus 1. All right? Now, we know that one other thing actually I want to write on this. I want to split this into 2 to the k. I want to be adding 1 and subtracting 1 over 2 to the k minus 1. Now I could write that one as sigma of m equal, actually I want to take these 2 to the k minus 1 as 1. And let me see how I want to arrange this one. Times m and plus, so I want to, let me put the minus first here, and plus 1. m minus 1 and to the 1 plus 2 to the k all of dash over 2 to the k minus 1. And this is equal to m plus 2 to the k over 2k minus 1. Well, I want to show actually this one is an integer. Okay, so I want to show this is an integer. And to do this, first let's look at from here. We know that 2 to the k and 2k minus 1, these are relatively prime. So this is equal to 1. All right? So in other words, the 2 to the k does not divide 2 to the k minus 1. And this implies that actually m must divide 2 to the k minus 1 divides m. All right? So we have this is as an integer, and which makes so this implies that m over 2 to the k minus 1 is actually some integer. All right? Now, with this in here, we have so sigma of k is equal m plus another integer here. Okay? So sigma, what does this equation say? This equation states sigma of m is the sum of one divisor m of m and another divisor which is 2 to the k over 2k minus 1. And this is it, because that's what sigma of m is. Sigma of m is supposed to be the sum of the divisors, the positive divisors of m. And this equation is saying that m is 1 and here's the other one. And in order for this, this means that m has only 2 divisors. All right? So this implies I tried to finish up the argument in here because we said that what we have in here originally, because I said I want to show this is actually an integer. Well, we have the fraction which was in here, which is m over 2. We go back in here. Yeah, actually 2 to the power k over 2 to the power k minus 1. All right? So we have this. 1 is an integer together with 2. This will make it also another integer. Well, let me finish up. So therefore, m has only 2 divisors or positive divisors. This implies m must be a prime. Must be a prime. this number right here, which is the sum of the two divisors of m, positive divisors, 2 to the k over 2 to the k minus 1. This must equal to 1. Let me see here. Actually, I did goof in here. I supposed to have, I'm sorry. This one's supposed to be m. As I say, there's something totally wrong in here. All right, now this is m. Let me actually go back to this one in here. Let me write it from the very beginning and then show how we got this. I'm sorry. All right, we have sigma of m. To start with, we have this is m times 2 to the k over 2 to the k minus 1. And I said we're going to write this one as actually 2 to the k times, or m times, m times 2 to the k minus 1 plus 1. Then when we multiply m in here, we're going to come up with the first. So we come up with m times 2 to the k minus 1 over 2 to the k minus 1 plus m times 1 over 2 to the k minus 1. So now that 2 to the k minus 1 cancel out, so we end up with this one is equal m plus m over 2 to the k minus 1. And this one, which I have shown, this is actually as I mentioned. Then, I want to repeat the argument again. I'm sorry, because I wrote the divisors incorrectly. So this is statement, sigma of m equal m plus m over this. So this equation states sigma of m, which is the sum of the positive divisors of m of m is positive divisors of m, namely, actually these are divisors m, and the other divisor is m over them. All right, now let's continue from here. So it means that because, so this implies that m has only two divisors, has only two divisors, and this implies m is a prime. This implies m is prime, and the m over 2 to the k minus 1, this other divisor must be the 1, must be the trivial divisor. All right? Now from here we're going to conclude that the second factor and the product of n is of the correct form. So from there we conclude that m is equal 2 to the k minus 1. From this equation, when you cross multiply, you get this, and we just show that this is a prime. It's a prime. Therefore, yes, n is equal 2 to the k minus 1 and 2 to the k minus 1 has this form. So this is the form of a even perfect number. All right. Sorry for the steps in the proof of this, but I hope they are clarified. All right. The next thing we want to look at is, we see what next I want to be talking about here. This is special form, or this number, which is 2 to the k minus 1 being a prime, and to play an important role. And we're going to be studying these type of numbers, okay, of the form 2 to the n minus 1, all right? These are called Mersini numbers, all right? But we have the following remark in here. So, by theorem 11.1, to find an even perfect number, we need to find primes of this form. All right. And then multiplying this by 2 to the power k minus 1, it makes this one is actually a perfect prime. Now the question is, under what condition this number, I want to denote this number by m sub k. All right, and later on we're going to be using this terminology. This refers to Mersini kth number. All right, so under what condition this is a prime. We're going to show that if this is a prime, then actually k must be a prime. Okay, we will show if m sub k is 2 to the k minus 1 is a prime, then k must be a prime. The exponent. However, the converse of this, unfortunately, is not true. However, it is not true that if k is a prime, then m sub k is 2 to the k minus 1 is a prime as well. So this part is not true. So this one, unfortunately, is not. So otherwise, we would actually actually have infinitely many perfect numbers. All right? We're going to be talking about this a little more. Right? So we're going to say the lemma that actually even generalizes what we want to be showing it. Okay, so the next lemma will generalize this. We're going to assume, the exponent or the base is not 2, but any other integer, and it's going to be forced to be 2. So here is the lemma that we're going to be proving. If a number like this is prime, then, or where a bigger than or equal to 1, then, and, so I put k in here, k here, and k bigger than or equal to 2, then sorry, k is equal to, a is equal to 2, and k is a prime. So it's a little more general than I stated, okay? Because here, even the exponent, the base of this type of number must be, right? So two things, we need to show that a is equal to 2 in itself, and the k is actually is a prime. All right, so let's just start with doing the factoring. A k minus 1, we can write this is as a minus 1, which you can check by direct multiplication. This is a k minus 1, a k minus 2, a. Now the have this factor a to the k minus 1 plus a k minus 2. I know at least we have that k is bigger than or equal to 2, so there will be 2 terms at least in here, plus a plus 1. And since a is bigger than or equal to 1, so this is bigger than or equal to a plus 1, and this is definitely bigger than 1. So in other words, we have the a to the k minus 1 is a minus 1 times a number that is bigger than 1. Now, since we are saying this is a prime, is a prime, then we must have the this is bigger than 1, so the only way this can be true is if a minus 1 is the first factor is equal to 1, right? So this is a factorization, basically, of a to the k minus 1, and one factor is bigger than 1, so this must equal to 1, and this forces a to equal to 2. All right, let's go to the other direction. And we're going to do this by assuming k is not a prime and find a contradiction. All right? Next, we're going to show k is a prime. So by contradiction, let's assume that K is composite. And this means here we can write it as both of these are bigger than 1 and of course less than. Well, let's look at, since we already proved that the A is 2, so we're going to consider 2 to the K minus 1 is equal to the RS minus 1. And I can write this one as 2 to the R to the S minus 1 like this. And I'm going to factor this as 2 to the R minus 1, and then 2 to the R to the power S minus 1. And so, plus 2RS minus 2 plus 2 to the actually R plus 1. All right. Now we have the 2 to the R minus 1. All right. This one, since R is bigger than 1, so this is bigger than 1 since R is bigger than 1. All right. But again, since this is a prime, since 2 to the R minus 1 is a prime. And also we have the other number, actually goes over the other number, which is 2 or the other factor, S minus 1 up to 2 to the R plus 1. Also, this is bigger than 1. So this, now since this one is a prime, then we leave the contradiction. So this is the contradiction. We have written this as a product of 2 numbers each bigger than 1, and that is not true. So therefore, the only thing in here is incorrect. Is actually K is must be composite. So therefore, sorry, K must be a prime. All right, so K must be a prime. Now, let's consider the other way around. So remember that we said that if we have this 2 to the K minus 1 is a prime, then the exponent must be prime. However, the converse of this statement is not true. Now let's consider this M sub B equal to P minus 1, where P is a prime. Is it true that M sub B is a prime? The answer is no. Actually, it's true for P equal to, we list some of the numbers in here, 3, 5, 7. All right, this one implies MP is equal to actually even for 2, so this is then the yeah, M2 is going to be 3, and M3 is going to be 7, all right, 4 minus, oh, let's see here, 3, 2, 2, yeah, 7, and M5, this one is going to be 31, and M7, that's going to be 28, 127. And each one of these give us actually the perfect, the P1, the first perfect number, which is 6, the second perfect number, which is 28. There's the third perfect number, which is 496. And this is the fourth, which is 812. All right? Then are there for 11, which is the next prime. This one is 2 to 11 minus 1. This is not a prime. Turns out that the M11, or 2 to the 11th minus 1, it factors into 23 multiplied by 89. And the value of this is 2047. So this is not a problem. So in other words, it doesn't go the other way. In fact, the next question, of course, it depends, is this. How many are there finitely or infinitely many perfect numbers? Of course, this depends on, are there finitely or infinitely many primes of this form M sub P? All right? So here is the question. Are there infinitely many even perfect numbers? Remember, I mentioned that there is no known odd perfect numbers. It doesn't mean there does not exist any. So far, nobody discovered any odd perfect numbers. In fact, in the next section, we're going to get sort of, if there were to be, to find one, what kind of properties such, odd perfect number satisfy. It's very, very strange kind of argument to look for properties or properties of numbers that nobody actually seen, what kind of condition they need to satisfy. All right. Well, so of course this one depends on. So this is true if there exists infinitely many what is called Mersini. Let me see here. Mersini primes. Writing the name in here. It is E. Mersini prime numbers. Namely these. Good to the power B minus 1, where B is a prime, and M sub B P is a prime. Remember we say that not every M sub P is a prime. But in order for this to be a prime, exponent must be a prime. But the number could be actually composite. So if there are, in other words, if there exist infinitely many Mercini numbers, so that for a prime P and M sub P is itself is a prime, then there would be infinitely many even perfect numbers. Because if this is true, then we have M sub P, which we can write it as 2 to the P minus 1 times 2 to the P minus 1 becomes perfect. Now, there's a lot of evidence that this conjecture, in other words, nobody know if there are infinitely many Mercini primes or not. But there is a strong evidence that this conjecture is true. Okay? So with this being true, this means there is a good possibility there are infinitely, many even perfect numbers as well. All right? And this brings us to the looking at some properties. Those, from the evidence we looked at, we said that the even perfect numbers ends with 6 and 8. It turns out this is true, but they don't alternately do that. Yes, it ends 6 and 8, but not in the way they conjectured it. A couple of theorems on this. The first one is theorem 11(2). And it says that an even perfect number ends in 6, means its units are 6 or 8. And again, this is equivalent to saying that if n is an even perfect number, then n either n is congruent to 6 mod 10 or n is congruent to 8 mod 10. So this is the same as saying that the units digit or an even perfect number is 6 or 8. And the proof is very straightforward, actually. Remember that we know from previous theorem, n has this form. 2 k minus 1, where k is bigger than or equal to 2, and of course the 2k minus 1 is a prime. Now let's look at the case if k equal to 2, then n is going to equal 2 to the 2 minus 1, 2 squared minus 1, and this gives me 2 multiplied by 3, this is equal to 6, and yes, it's true. So this one is congruent to 6 mod, or it ends in 6. Now let's consider the case that where k is bigger than 2. Now consider the case where K bigger than. There are two cases to consider. Two cases depending on K. Since we have K is a prime, okay? Since K is a prime, this implies K is congruent to 1 mod 4, or K is congruent to 3 mod 4. So these are the only primes if we're going to have either one of these forms. So let's consider the case 1 where K is actually congruent to 1 mod 4, and which makes that the K is equal 4m plus 1 for some m. And let's look at what the n is going to look like in this case. All right. In this case, n is equal to, remember, 2k minus 1, 2 to the k minus 1 is equal 2 to the 4m. And 2 for m plus 1 minus 1. Yeah, let's multiply this out, and this becomes 2 to the 8 m plus 1 minus 2 to the 4m. And this is equal to 2 to the 4 to the 2m multiplied by 2 minus 2 to the 4 to the m. And this is equal 16 to the 2m multiplied by 2 minus 16 to the m. Now I claim that this 16 to the m is actually congruent to 6 mod 10. It is very simple to see. Here's the simple claim. 16 to the m is congruent to 6 mod 10 for any m bigger than or equal to. This, of course, follows, of course, 16 is congruent to 6 mod 10. Actually, this one we have to do by more like by induction, okay? Or so by induction on m. So for m equal 1, yes, this holds, of course. And let's assume it's true for m. Assume that 16 to the m is equivalent to 6 mod 10 for some m bigger than or equal to 1. Then let's look at 16m plus 1 times 6. That 16 to the m, this one is congruent to 6, then multiply by 6. And this one is congruent to mod 10, like this. See what I'm saying here. No, I'm sorry. I want to write this is 16 here. I should say something is wrong. I'm 16. So the first one is congruent to 6. All right, and 16, I'm just going to keep it 16. All right, mod 10. And when you multiply this, you actually can write it as 6, 10 plus 6. And this gives us 6 times 10 plus 6 times 6. Actually, let me make the, okay. Let me make the middle one here. This one is congruent to actually this one is just 96 and this is congruent to 6 mod 10. But so since this is true for m plus 1 by mass induction, so this one actually holds, so we have this is true. Now let's go back to the n, what's equal to finally we have the n, so we have n was written as 16 to the power m times 2. And then we have minus 16 to the m. Actually more like, let's see here, 4m. And this one is m. Oh, but again, each one of these, this one is congruent because it's true for any m. So to the 4m, this one is congruent to 6. And this one is congruent to another 6. Altogether, this is congruent to 6 mod. And actually, this one gives us what is, when do we get 6? When we get the form of the prime is 4k plus 1. Now, case 2 we're going to consider is when k is congruent to 3 mod 4, which makes the k equal 4m plus 3. And a very, very similar argument actually proves the same thing. So in here, the n is going to be 2 to the power 4 m plus 3 minus 1, so this becomes 2, and multiplied by 4k plus 3 minus 1. And again, just multiply these out and simplify, you're going to get 16 to the power 2m plus 1 minus 4 times 16 to that. So after you multiply and make them as power of 16, now you're going to apply the same thing. This is congruent to 2 times 6 minus 4 times 6. And altogether, this gives me negative 12. And this is congruent to 8 mod 10. All right? All right. Actually, when you look back at those numbers, they're known to the Greeks, you find the last two digits. When the last digit is 8, is actually the 10th digit is 2. Means they end in 28. All right. Remember that we have these are the. Let me go back in here. We have P2 is 28, and we have P4. The fourth perfect number is this. So in other words, they end in 28. And it turns out this is the case. Means, we could actually strengthen. Means the result that we obtained by saying that when K is congruent to 3 mod 4, then that and n is equal to the k minus 1 is a perfect even number, then it ends in 2A. All right, we're going to prove this. We're going to prove a stronger result, basically. And here it is. Okay, so I'm just going to prove this. The idea is actually this. We're going to consider this case, and I have this claim that under this, when n is actually of this form, congruent to 3 mod 4, I claim that n is congruent to 28 mod 100. All right, and with this, then we would actually have this is a proof that it ends in 28. And the proof goes like this. And again, we're going to look at 2k minus 1. This is going to be 2 to the power of 4m plus 2. And this is equal to 16 to the power m times 2. And this one is congruent to, because 16 to the m is congruent to 6 mod 10. So we have this congruence relation. And actually, this is 4 in here, not 2 squared. 4. And this is 4. And this one is 24, right? And this is congruent to 0, so 4 mod 10. Sorry. All right? So we conclude out of this that for every k bigger than 2, consider the case when we get 8 actually, we have, that's what this is equivalent to, we have 4 actually divides the 2 to the k minus 1, all right, or equivalently, we could say this one is 2 to the k minus 1 is congruent to 0 mod. You see what? So let's put it together. So we have this congruence and this relation for every k bigger than or equal to 2. Of course, 4 is going to divide this, which is equivalent to that. So the first congruence implies that 2 to the power k minus 1 ends in 4. So 2 to the k minus 1 congruent to 4 mod 10 implies that the, let me see how exactly I'm going to write this one, that the last digit of this number here is 4. And 4 divides this 2 to the power k minus 1. This itself implies that the number formed by the last 2 digits is divisible by 4. Now, if we put these together, then this means that the so this implies that the 2 to the power k minus 1, the last 2 digits in this, all right, it's the same as saying this one, it must have a unit digit of 4, and to be divisible by 4, then we have 0, 4, or 4, 4, 2, 4 also, sorry, divisible by 4, and it has its first digit is 4, then 4, 4, then 6, 4, or 8, 4. And this is mod 100. Same thing in the last 2 digits, is that this one is 100. Now, let's make this one 2 to the k. This is actually 2 to the k, I'm sorry, not 2 to the k minus 1. Let me see what I have in here. I'm mixing this up. No, this is right. This is k minus 1. All of these are k minus 1. Now, let me look at what is 2 to the k minus 1, the other part of the perfect number. So this one is going to be 2 times 2k minus 1 minus 1. And if I multiply the forms of these, or write them as mod 100, so this is going to be 2 times 4 minus 1, or 2 times the 24 minus 1, or 2 times 44 minus 1, 2 times 64 minus 1, and 2 times 84 minus 1. Mod 100. And now we do all the calculation in here. This becomes 7 here. This one is 47. This one is 87. Then we have 27 mod 100, because we are reducing, or this one is 67, the last one. Now together, then therefore we take n, which is 2 to the k minus 1, 2 to the k minus 1. Then we need to multiply these together, 7 and 4, then multiply 24 and 47, and multiply 64, let me see it here, 44 times 87, then 64, 27, and finally 84 with 67. Each one of these, it turns out to be congruent. All of these products, they're going to be congruent to 28 mod 100. All right? So I hope it's clear when I've done all these small numbers in here, but the argument is really very, it's just a matter of doing the correct thing on the right time. Like, you know, if I did this correctly at the right time, but that's what it is. All right, so we have then whenever the k, the exponent of on the 2 in here for an even perfect number is congruent to 3 mod 4, then that perfect number actually ends in 28. All right, and this is it for this lecture. And I'm going to do another section from chapter 11, all right? And that is Mersini primes, because they are related to perfect numbers. And then I'm going to be doing one section from chapter 12, that is the Pythagorean triples, or Pythagorean numbers. And then at least one section from chapter 13. All right, and that's to do with, you know, which numbers can be written as a sum of 2 squares. All right, and we'll see if we could do also when the number is a sum of 3 squares and 4 squares. All right, okay.